In this video, we're going to look at more examples of areas between curves. Consider the case of finding the area between the curves y equals f of x and y is equal to g of x, where f of x and g of x intersect at two or more points. So you can see there's an intersection point here at x equals c, and there's another intersection point at x equals d. So we actually have to break it up into three separate regions, and the integral from a to b f of x dx would be equal to the integral from a to c. Now the top function is f of x, the green function, minus the bottom function, which is g of x, and integrate with respect to x, plus, now integrate from c to d, but notice now the top function is the gray function g of x, minus the bottom function, which is f of x, plus, now integrate from d to b, but now the top function is f of x and the bottom function is g of x. F of x minus g of x dx. We can also write it more compactly as the integral from a to b, absolute value of f of x minus g of x dx. Alright, so the notation absolute value of f of x minus g of x, this is equal to f of x minus g of x when f of x is larger or equal to g of x, and it's equal to g of x minus f of x when g of x is larger or equal to f of x. So the area bounded by the curves y equals f of x and y equals g of x and x equals a, x equals b is given by area is equal to integral a to b, absolute value of f of x minus g of x dx. So we can write the area as a definite integral. Area is equal to integral from a to c, top minus bottom, f of x minus g of x dx, plus integral from c to d, but now g of x is on top, so that's g of x minus f of x dx, plus integral from d to b, and the top function is f of x minus g of x dx. And we have the rectangular slices here, so you can see for the first integral, the height is f of x minus g of x, given by this height here. For the second integral, the height is g of x minus f of x, given by this rectangle here. And for the third integral, the height is f of x minus g of x, given by this rectangle here. And if you look back at a diagram, it makes sense. Here we have, right here, we have g minus f. That's the second rectangle, g of x minus f of x. All right. Let's look at an example. Find the area of the region bounded by y is equal to 2x over 1 plus x squared, y equals x squared, and x equals 0, x equals 2. So the first thing we'll do is find the intersection points of y equals x squared and y equals 2x over x squared. Sorry, 2x divided by 1 plus x squared. So we have y equals y, make the two y values the same, and solve for x. So what we get is 2x over 1 plus x squared is equal to x squared. Let's write this over 1 so we can cross multiply, and we're going to get 2x is equal to x squared plus x to the fourth. If we bring everything to one side, we get x to the fourth plus x squared minus 2x equal to 0. Now let's factor out an x. We get x times x cubed plus x minus 2 equals 0. So one solution clearly is x equals 0. But now we have to solve these cubic polynomials, and these are often tricky. There is no algebraic way of solving that, so we just have to make a good guess. So a good guess would be x equals 1, for example. Let's try that. X equals 1, and if we plug this in, what do we get? We get 1 cubed, which is 1 plus 1 minus 2 equals 0. it works. That means x equals 0 and x equals 1 are the x-coordinates of intersection. Of course, we can find the y value. Y is x squared, y equals 1. And you can put it into either function. Doesn't really matter because they're intersecting at that point. And x equals 1, y equals 1. Sorry, let me fix this. X is 0, y is equal to 0. Because we're putting into y equals x squared. All right, so x equals 0, y equals 0. That's one of the intersection points. And x equals 1, and y equals 1. All right, and this is x of intersection. And we found both x and y. All right, so now let's sketch the bounded region. We've sketched it here. We had to scale up the x-axis just to make this graph stand out so we can see all this main feature. But the main takeaway from this is that to the left of x equals 1, you can see the top function is 2x divided by 1 plus x squared. And the bottom function is y equals x squared. To the right of x equals 1, the top function is y equals x squared. The bottom function, the bottom point of contact of the rectangle with the curve, is y equals 2x over 1 plus x squared. So you can see how the integral has to be described separately in the two different regions. So we'll have one integral from 0 to 1, 2x over 1 plus x squared minus x squared dx. And this definite integral represents this shaded area here. Plus, then we integrate from 1 to 2, but now the top function is a parabola x squared, and the bottom function is 2x divided by 1 plus x squared. And this is this region here. All right, so now let's set up the definite integral to find the area of this region. We know that the points of intersection of y equals 2x over 1 plus x squared and y equals x squared are x equals 0 and x equals 1. Now notice that 2x divided by 1 plus x squared is larger than x squared when x is between 0 and 1. We can clearly see that on the graph. 2x over 1 plus x squared is larger than x squared when x is between 0 and 1. And conversely, we know that x squared is larger than 2x divided by 1 plus x squared when x is between 1 and 2. So therefore, the area of the bounded region is equal to integral from 0 to 1, 2x divided by 1 plus x squared minus x squared integrated with respect to x plus integral from 1 to 2 x squared minus 2x divided by 1 plus x squared dx. So the key point here is you have to describe the two regions differently. There are two separate integrals because there's an intersection point, and to the left of x equals 1, 2x over 1 plus x squared is the top function. Whereas to the right of x equals 1, the top function is y equals x squared. So that's the reason that we had to do two separate integrals. All right, so now we have to solve these integrals. So we have integral from 0 to 1, 2x over 1 plus x squared minus x squared dx. That's the first integral. And the second integral is x squared minus 2x divided by 1 plus x squared. Let's do this one first, 2x over 1 plus x squared, because that's going to involve U substitution. So we let U be equal to 1 plus x squared du is 2x dx. So integral of 2x over 1 plus x squared dx will be integral 2x dx is replaced by du over u. That's going to give us log of u plus c, and that's basically log of 1 plus x squared. We don't need the absolute value because inside the brackets is positive. All right, so the area is going to be, let's split up the integrals. Integral from 0 to 1, 2x divided by 1 plus x squared dx minus integral from 0 to 1 x squared dx plus integral from 1 to 2 x squared dx minus integral from 1 to 2 2x divided by 1 plus x squared dx. We already know this antiderivative, we solve for it, so the area is going to be equal to log of 1 plus x squared, evaluated from 0 to 1. And antiderivative of x squared, that's just going to be x cubed over 3, evaluated from 0 to 1, plus x cubed over 3 again, evaluated from 1 to 2, minus, and this one we already evaluated using U substitution, this is log of 1 plus x squared from 1 to 2. Now there's a lot of moving parts here, so we just have to be careful. It's a very simple thing to do, but easy to make mistakes. So let's put in the upper limit, applying fundamental theorem of calculus. We get ln of 1 plus 1 squared, that's log of 2, minus log of 1 plus 0 squared, so that's log of 1, minus, and now we're going to put 1 in, we get 1/3, minus 0, plus, put 2 in, we get 2 cubed over 3, that's 8 over 3, minus 1 over 3, minus log of 2 squared is 4 plus 1 is 5, minus log of 2. Let's open this up. We get area is equal to log of 2 and minus, well, log of 1 is 0, so that's just minus 0, minus 1/3, plus 8/3 minus 1/3 is going to be 7/3, minus log 5, distributing the minus sign, plus log 2. Very easy to make mistake. You really have to distribute this minus across the bracket. All right, let's simplify this. We got log 2 and log 2, so they add up to 2 log 2. We have 7/3 minus 1/3, that's 6 over 3, that's just plus 2. And we have minus log 5. This is the area of the shaded region. If we go back to the diagram, we'll see that we have found this area. This whole area, which is basically all of this, and all of this. The hard part was the fact that we had to split it into 2 separate integrals. All right, and this is the entire area right here. Okay, thanks.